Hello students, today we'll be discussing about theory of simple bending. Before deriving the equation, we have to understand some of the assumptions to be made for the theory of simple bending. Uh, the assumptions are, first assumption is, the material of the beam is perfectly homogeneous. That means it should have equal elastic property in all directions. Then the beam material is stretched within its elastic limits. That means it should obey the Hooke's law. Because within the elastic limit, the material always obeys the Hooke's law. That means within the elastic limit, the stress is always directly proportional to strain. Next, next is the transverse section, which are plane before bending, remain plane after bending. Suppose this is our bar, and this is our bar, and this is its transverse section. So before bending, it is plane. After bending, this transverse section will also remain plane. Next, each layer of the beam is free to expand or contract independently of the layer above or below it. Then the value of Young's modulus should be same in tension or for compression. Next point is the beam is in equilibrium. That means there is no resultant pull or push in the beam section. Let's take a cross section A, B, C, D. So in this cross section, a segment that is EF will be taken for the consideration. And this EF is y distance away from the neutral axis. Okay, so at the neutral axis, there is another section that is GH. Okay, so this is the before bending situation. After bending, an arc will be created uh, of radius of curvature. This is R, and this is the angle of curvature, that is theta. Okay, so during bending, there will be a layer which will be neither shortened nor extended. Okay, so this layer is called as your neutral layer. Then the line of intersection of neutral layer on the cross section is called as your neutral axis. And take, so our segment is EF. Okay, this is the before bending condition. After bending, there will be some change in length. So final condition is E dash F dash. So E dash F dash will be equal to the radius of curvature and the angle of curvature. The radius of curvature up to E dash F dash is, this is the distance R and this is Y. So it will be R plus Y and theta is the angle of curvature. Okay. Where R is the radius of curvature and NA the neutral layer. So at the neutral layer, NA remains same. So the segment presented in the neutral layer, that is GH, will also remain same. So GH will be equal to G dash H dash. That is nothing but, this is the radius of curvature, that is R, and angle of curvature, that is theta. So GH is equal to G dash H dash, that is equal to R theta. GH is equal to G dash H dash because it is presented at the neutral layer. Okay, because at the neutral layer, no tensile force is acting, no compressive force is acting. Now let's calculate what is the change in length on EF. So E dash F dash is the final condition and EF is the original length. This is the final length. This is the original length of our segment. So E dash F dash will be nothing but R plus Y theta and EF is equal to R theta because here you can see EF is equal to GH. Okay. And GH here is equal to R theta. So in place of EF, I can write the R theta. Okay. So here R theta and R theta can get cancelled. Then we will get Y theta. The strain in EF is equal to change in length to the original length. So change in length we have calculated in previous slide, that is Y theta, and original length, that is nothing but EF, that is equal to R theta. So by cancelling theta we will get Y by R. From the Hooke's law, we know that Young's modulus is equal to stress to the strain. From that, we can get strain is equal to stress divided by Young's modulus. Strain is equal to stress to the Young's modulus. That is nothing but sigma to E. In equation 1, we got strain is equal to Y by R. By equating the right hand side, we will get sigma by E is equal to Y by R. Now let's take an area dA which is present at the y distance from the neutral axis. Okay. From the equation 3, what will be the sigma value? Sigma value will be equal to Y by R into Young's modulus. That is equation 4. Then force on dA, so this elemental area, there will be a force acting on it. So it will be equal to, force is nothing but stress into area. So area we have taken as dA and stress is sigma. So in place of sigma, we will write Ey by R and dA will be the elemental area. Okay. Next, the moment of resistance offered by this elemental area is equal to moment of force about the neutral axis. Okay, because of this distance. So movement is nothing but force into distance. So force is nothing but Ey by R into dA and distance is y. So from this we can get E by R y square dA. This is for this small elemental area. The total moment of resistance offered by the whole section can be equal to E by R, that is a constant, we have to take it out. Then integration of y, then integration of y square dA. Okay. The integration of y square dA is nothing but moment of inertia. From this, we can get M by I is equal to E by R. Here I is the moment of inertia. So from equation 3 and 4, okay, we can get sigma by y is equal to M by I is equal to E by R. Okay. So in equation 3, we got sigma by y is equal to E by R. And in equation 4, we got M by I is equal to E by R. By combining these two equations, we can get sigma by y is equal to M by I, that is equal to E by R.